go ahead and get into some of the new stuff. So to give ourselves a little bit of a running start, the first thing is our definition of a planar graph. And let me make this out to its 100% size. So a planar graph is simply a graph where you can draw it on a piece of paper and draw it in such a way, so you put the vertices on the piece of paper in such a way that none of the edges are going to cross. Now, is it okay to curve your lines like what we did on this example yesterday? Yep, totally fine. Okay. Do we try to get straight lines for our graphs? Yep, but it's okay if they're curved too, and we're going to see that today. Now, if you start off with a graph where the lines cross, like the two examples that we looked at last time, and then you redraw it so the graph then doesn't have crossing lines, there is a distinction. Both of the two graphs are still called planar graphs, but once you redraw your graph so that there's no crossing edges, that is, oh, scrolled too far for you guys. That non-crossing edge version of the graph is called a plane graph. Okay. Now, if you started off with the non-crossing edges, it's still called a plane graph. And then we ended last time on the definition of dual, so I wanted to go ahead and start off today with one more example of finding the dual of a graph, because we just did the one example last time, although let's face it, it's going to be doing the exact same thing that we ended with that last example. But to get there, let's relook at the definition of a dual. A dual of a graph is where you flip-flop your vertices and your faces. So remember, a face is, well, there's two types. The normal type of face, or the most common type of face, is what's known as a bounded face. It is, it's a circuit where you're looking at all of the region inside the circuit. Your book actually doesn't use the official term for a face. He just uses region, which is a descriptor, and that's totally fine. And in the formulas that we have, where we used F for face, which is actually the official formulas, he uses R for region. Same thing. I don't know why he didn't use the real name. He just used the description of it instead. Okay. Now the unbounded face, this one is what makes actually all the formulas work out correctly. This is, again, a closed circuit, but it's the closed circuit of all the edges around the outermost part of your planar graph. So first, you really, in order to form the dual or even to count your faces, you typically redraw your planar graph in its plane format. So as a plane graph, where all the edges don't cross. If all the edges don't cross, there's one circuit that'll go around the exact perimeter of your graph. Perimeter is not a technical term for graph. It is a description. And then that unbounded region is everything outside your graph. Okay? Now, we did this example here last time where we said, hey, we have some graph. The graph was given to us in red. Every single face, we had 3 bounded faces right here, turned into vertices. I went ahead and labeled them F and then the subscript, which is common convention. And then the unbounded face, we went ahead and labeled it with an F for face, and the infinity sign at the bottom indicates the unbounded face. Infinity because it's not bounded. So 2 questions just came in. The first one is, does every graph have a dual? And the answer is no, but every planar graph, you can find a dual for it. And that's one of the reasons why when you go back into the definition, it does require you to start off with a planar graph right here. Now, multi-graphs that are also planar, that's totally fine. They will also have duals. The key thing here is you have to be able to draw your graph with the edges not crossing. And the second thing is, yes, if you take the dual of a dual, you will get back to the original graph. Or the second question there. Where were we? Right. So one of the things that we noticed, and this is where I need to change the size because we did this at the end of last time. One of the things to notice here is the count in terms of the number of vertices, the number of edges, and the number of faces. This will be a big deal later on, but right now it's just the bare minimum in terms of the relationship. Notice for the dual, because you convert each face into a vertex, the number of faces in the original graph is the same as the number of vertices in the dual. And remember how we found our edges? We found our edges in the dual by crossing, so perpendicular to each one of the edges in the original graph, which means there's a one-to-one mapping between the edges in the original graph and the edges in the dual, which means there's always going to be the same number of edges between the 2 graphs. And same deal with vertices. One of the things you can actually think about is notice where the vertices are in the original graph, so A, B, C, all the way down here to F. Those guys are actually inside each of the new faces on your dual. So it turns out the number of vertices here is going to end up being the number of faces down in the dual. And notice that does require you to go ahead and count your unbounded face in the dual as well. And that is because vertex B right here, notice it's not inside of any other loopy edges. B would be mapped here to your unbounded face if you were mapping. So that's the running start. Let us get to a new example. Oh, I guess I should have actually moved that information down here. In our next example that we've got right here, it doesn't have any directions, but the directions here is let us go ahead and find the dual of this graph. Now, I forgot to actually put labels on these vertices, so let's do that real quickly. Ooh, okay. Let's deal with that question in just a second. So the question that came in is, what do you do about loops if you're dealing with a multi-graph? So let me actually move this example up a little bit, and we'll do an example after this first one that is where you start off with a where you start off with some loops in the multi-graph. That's a little high. Let's put a little bit of a space. All right. So firstly, let me go ahead and label these vertices. That way we can talk about them, and then we'll start thinking about the dual. So if you're writing this down on your own, we should have plenty of time to copy it out. I just went ahead and labeled these guys around the outside. So now we're ready to go ahead and think about creating the dual. So first thing that you'd want to do in creating a dual is you want to identify all of your faces. So sometimes what people like to do is they actually like to identify everything first. So they look at the number of vertices, the number of edges, and the number of faces. Later on today, we'll actually have the technical term for number of faces as well, but we'll do that a little bit later. So number of vertices here looks like it's what? What is that, 5? That looks like 5. Okay. Anybody spot how many edges we have? It's at 8. It does look like 8. Okay. And since I actually figured we'd have something like this, I went ahead and if you found it, let me go ahead and share this with you guys. See if you can't find the number of faces as well. That way everybody gets a chance to answer here. So this is for the graph we're actually currently on. I guess actually I could do it for any graph since I didn't get the picture. That also allows me to sneakily here reorder my screens that went all haywire a second ago. All right, there's still a couple people who haven't made a guess. I'll hold that for just a second. That way everybody can have a guess at once too. All right, so while the last looks like 4 of you are figuring it out, let us start looking at where some faces are for sure. So faces are what? Faces are where you're looking at, if this was a polygon, it would be like sides. If this was a polyhedral, remember polyhedral would be something like a cube. When we talk about faces, that's exactly like the sides of that polyhedral, if you will. Now, we're talking about graphs. We're not in geometry here, although the terminology does have some crossover. And we want to start looking at the different things. Remember what we're looking for circuits. So for example, if we start labeling these guys, maybe we call this guy right here of AED, face 1. Now note, if you don't have your graph in its plane graph depiction, and it's still a planar graph, you can actually find your faces even when the edges cross by looking for all of your different circuits. Now the issue there is, notice there's a circuit AD, B back to A, and that guy isn't a face. So there is definitely easier to deal with this if you're in the plane graph depiction. Now another face we can label, we can go ahead and label this guy F2 on the face that's represented by the circuit BDE back to B. And then we can maybe F3, the circuit ABE back to A, and maybe F4, the circuits that is BCD back to B. So the question, of course, is, how many circuits did you guys think we had? Let's actually look to see how you guys did. So it looks like most of you are split between either 4 or 5 faces. Yes, one of the correct answers is either 4 or 5. So it turns out in this case, as we just labeled them, there are 4 bounded faces right there. And don't forget, you also have the one unbounded face that's over here to the outside. Now, when you make your dual, if you don't have the unbounded face, you're going to lose a lot of edges because that's where typically a lot of edges come in. It's also typically where when you're dealing, we're actually going to talk about Euler's form a little bit later today, so hold on that question here for just a second. Probably lost my train of thought there for a second. Sorry about that. If you don't have the unbounded face, not always, but this often takes your dual and deletes out some of the extra edges that makes it a multigraph. Now that being said, not always. Okay? It all depends on what the structure is of your actual graph. Okay? Let's put in some edges here. So if we're trying to find the dual, you want to make sure you put in the little dots that represent your new vertices, which are coming from each of your faces. So what are some edges that I should put in this dual? Anybody have a guess here? There's a bunch of them that's going to come in. Anybody spot one of them? DA. DA technically is an edge in the original graph. If you're dealing with edges in the planar graph, you want to deal with it off of the faces here. But I'm assuming you mean the edge that crosses DA. So assuming that's the case, you're going to go from F1, and we'll pull all the way out to our unbounded face. And then we can do the same thing with a lot of the other ones. You could do the same thing, say, with F3, cross AB, and get to your unbounded face, or the vertex that is now representing the unbounded face. Let me see. I'm reading your question. So ADE, yep, that would be a face. ABE, yep, that's face. DC, DCE, so this one right here is a face. I feel like I'm missing one of the ones that you wrote down. Oh, this one right here. Yes, all 4 of those are faces. The big one right here. So faces are dealing with regions. So you're dealing with when you're looking at your face, it is not just a circuit, because if you deal with any old circuit, it's not actually going to work. It's a circuit where if you look in the region that the circuit is dealing with, so this is true of your bounded faces, you can't have any vertices inside of it. So here, ABD would totally be a circuit, so that part's fine. But inside of this circuit, you actually have right here a vertex. So that guy would not be considered a face. So if we, actually, let me put it over here to the side. I feel like I'm going to regret this in just a second, but we'll go with it as long as it makes sense. So suppose you have somebody like this. And I'm actually going to pull almost the exact same graph that we have, except leave off vertex C. That's the only thing I'm changing. E. Now, looking at this guy as a planar graph, it is flat. It is two-dimensional. It's only on the piece of paper. Okay? So here you've got your, and I'm going to color code them for us, so hopefully this helps. you've got the face that's right there, so AED. You've got the face that's ABE. And then you've got the face that's, hopefully this works. Oh, that's not a very good nether color because that's really close to that weird purple color. And then that one down there, that's the BED. Okay? I've got another question that came in. DE, where's DE? If DE didn't exist in the original graph over here, then the face that's currently labeled as F1 and F2 would be one big face. That's a good question. To some extent, it actually depends on how you've drawn the plane graph depiction, because I see that I see your point in terms of being able to redraw it. Oh, yeah, sorry. Here, this should get much bigger now. Whoops. Should see it now. What's going to happen, and we're going to get to this formula in a little bit, the formula will actually tell you that there's a set number of faces. If you have X number of vertices and Y number of edges, and you're a planar graph, there's actually a formula and you can solve for how many faces there actually are. Okay? In terms of this particular case right here, when you guys are looking at the ABD, or over here when I redrew it without this bottom bit, yeah, that large guy is actually split into smaller faces, if you will. Although if you actually get rid of the bottom part, and this is what I was attempting to show you guys, but we haven't gotten there yet, you actually have a face, the unbounded face in this situation, that would be represented by the A, the B, the D. Okay? But the key thing here is when you deal with whatever your face is, and that was a terrible idea with a highlighter there, distracted myself again, is whatever you've pulled for your face, it's going to be a circuit, but inside of that circuit, so where you want to sheet it to be your face, unbounded guy, outside the graph, there's no vertices outside the graph. For a bounded face in here, you're not allowed to have any vertex inside of that region you're trying to call a face. Okay? In this one here, what I wanted to show to you guys, if you think about this as a three-dimensional depiction, not what planar graph means, but if you try to visualize this as a three-dimensional guy, this is called a tetrahedron, where you've got 1, 2, 3, and then A, B, C would be like the face, would be like the side that's closest to what we're currently seeing, and that would be basically a pyramid that has 4 sides that are all triangles. Here, notice the unbounded face represents the A, the B, the D, the part that's closest to us. So that's one of the things that's going on behind the scenes, is it's like grabbing some of those outside bits if you popped it into 3D. That only works if you have a certain number of faces, though. It does not actually work in all cases. You'd have to go up to higher dimension. And I'm not assuming that any of us can visualize things in like 10 dimensions. Okay? But there are some other stuff going on behind the scenes here. But the key thing to remember, so ignoring all of that extra expose right there, the key thing to remember is when you're trying to grab a circuit for a face, don't have any other vertices inside that circuit, inside that region you want to call a face. I know I probably said way more than you guys ever need to know, but did that make sense? Did that answer the question that you guys had? Clearer on identifying who faces are if you're given the plane graph depiction. All right, it looks like it's better for a couple of you guys. Okay, so going back to our guy, going back to the original red graph right here, let's go ahead and put in the extra edges. So I'll go ahead and put in all of the edges that are going to cross our outside or our boundary lines of the entire graph. So we'll look at the edge that goes through BC. We'll look at the edge that goes through CD next. Oh, make sure I have the right thing. And these are the only edges. Whoop. These are the only edges that actually go to the vertex that was created from the unbounded face. Now, Once we have those edges in play, every other edge, notice, is only going to cross edges that are inside the original graph. So what are some other edges that we can put in this dual? Anybody spot some other edges we can put in the dual? In other words, if you forgot about the unbounded face, what are some edges that you would still get in the dual? Yep, you could have an edge between F1 and F2. I see a couple of you guys grab that one. So that edge. You can also get one from F4 to F2. Yep. There's another one. Anybody spot some of the other ones? There's actually two more. Yep, the ones joining to F3. So F3 to F2 and F3 to F1 with these guys. Now at this point, once you have these dotted lines that cross every single edge in your original graph, you have the dual, as long as you didn't do anything weird. Okay? So this means we have all the edges that we need in the dual. And if we go ahead and redraw our dual, so it looks like a proper graph with no dotted lines, I have a tendency to put the unbounded edge or the vertex that represents the unbounded edge near the top, but you don't have to. It just has to be somewhere. And then maybe we do something like, I don't know, maybe F1 is here, maybe F3 is here, maybe F2 is there. I definitely should have drawn it like that, and maybe F4 is there. All right, so that'll untwist it a little bit, but oh well. So here, if we put in the edges, we had the, what? F1, F2, F3, we're going to have form a little triangle. We had F2 and F4 connect with each other. And all the other edges in the dual are going to connect to or be incident to the vertex that represents your unbounded edge. And there's 1, 2, 3, 4. And these 4 edges, double check that it's 4, these 4 edges are going to connect back to the other 4 vertices. Now, watch out, it's not perfect here. Okay? So these top 2 dotted line edges go to F1 and F3. So F1, F3. But these 2 dotted edges don't go to F2 and F4, they both connect to who? Anybody spot where the other endpoint is of these bottom 2 dotted lines? Yeah, they both connect back to F4, and that's because the fourth face right here has 2 edges that deal with the outside boundary of this graph. So that means here we actually have a multi-edge. And this would then be drawing the dual without all of the extra craziness. And if we change the orientation of this guy a little bit, maybe we could have had less curved lines, but with a multi-edge, you always have a little bit of a curve there. So let's double check that we actually get the same numbers, but in reverse. So double checking here, did we actually get 5 vertices like we were supposed to? Yep, it looks like we got 5 vertices. We were supposed to get 8 edges. Check out the dual. Do we actually have 8 edges? Yep, it looks like we've actually got 8 edges. And one of the keys here is when you count up the edges, make sure you count your multi-edge 1, 2, or just kind of just 1 edge. And lastly, we need to have 5 vertices. We saw that last time that there should be some symmetry here. Now, actually, it's already symmetric, so we definitely should have 5. So if we look here and we count up our faces, we would have 1, 2, 3, 4 bounded faces, plus the 1 unbounded face. So yes, that does give you the total of 5 faces. And I'm not going to lie, I personally, as well as what most people have told me when they're first learning about it, when counting faces, it's often easier to count them in this sort of 1, 2 setting where you count up all your bounded faces and then put that plus 1 at the end. Okay? So questions make sense, kind of feeling a little bit okay. All right, so there was a question of what happens if you try to do this on a planar graph, but the planar graph starts off as a multigraph. So I'm just going to do a really baby example. and let us make this red so it looks the same as the other examples. Suppose you had something like this. So a super, super tiny guy, okay? Like literally about as tiny as you possibly could with a multigraph. And let's go ahead and label this guy too with A and B. I guess we don't have to, but went ahead and did it. Now, when you're looking at this guy, this original graph, how many vertices does it have? How many edges does it have? And then we'll look to see how many faces it has. So in this one, hopefully you're all thinking it has 2 vertices. So how many edges does it have? It's got 3 edges, and yes, it does have 3 faces. It's got 1 face inside the multi-edge, 1 face inside the loop, and 1 face up there, which is our unbounded face. So this is 2 plus 1, or a grand total of 3. Now, if we look at the dual, let's go ahead and label these guys. We have F1, F2, and then F infinity. And let me blow this up a little bit so you guys can see it better, since those F1 and 2 got a little tiny. Okay. Now, when we put in the edges, remember, we're going to have how many edges that we're going to be dealing with. Anybody have a guess? How many edges should we have in the dual? It looks like the majority of the, it's a little all over the place, but the majority of the guesses so far are at 3. And for those of you who guessed 3, yes, you're correct. And here's how you tell. There's the same number of edges in the dual as in the original graph. So that tells us we're going to be looking for 3 edges. Why? Because we're going to have our dotted lines, when we draw them on top of this original graph, cross each one of our multi-edges. Each of the 2 multi-edges and the actual loop itself. Now, anybody have a guess on how many vertices we're going to end up in the dual? Right. We're going to have 3, and those are actually already labeled with our face numbers. And the last thing is the number of faces. Anybody have a guess on the number of faces in the dual? So this one would be the same as the number of vertices. So your number of faces, your number of vertices, and I flip-flopped them here accidentally, will flip-flop in the dual as well. And if you know that ahead of time, that gives you a leg up on making sure that you get your dual correct. Or you can check to see if your dual looks like it's on the right track. So here, if we start putting in our edges, notice there's going to be no edge between F1 and F2. Quick check. Why would there be no edge in the dual between face 1 and face 2? Don't overthink it. Yeah, the quickest thing here is they have no edge in common. They are sharing a vertex, but that doesn't matter. Okay? So since there's no edge in common between face 1 and face 2, no edge will be in common in the dual either. So notice in terms of all 3 of these edges, all 3 of the edges are touching the unbounded face and then one of the 2 bounded faces. So if we look at F1, we'll have 1 edge that goes through the top half of the multi-edge A to B, and the second edge would go through the other half of that multi-edge. And if we then look at F2, it's got a single loop. So here, we'll have 1 edge that goes through that loop, and so it's going to end up at the unbounded face. Now, putting this all together, if we draw this, I'm not going to draw it much different. I'm just not going to have the 2 graphs on top of each other. I'll go ahead and don't put an A. There's no A in the dual. If we go ahead and put our labels for our faces, so F1, F2 at the bottom, the unbounded face at the top, notice what happens. We get an edge from F2 to the unbounded face, and then there's a multi-edge right here from F1 to the unbounded face. Okay. So in this particular case, when we went ahead and found the dual, the loop completely disappeared. That's common. Sometimes you can pick up loops in the actual Duel, but if you have a loop in the original, it's common to have it disappear. And also here, in our multi-edge, that one actually stayed a multi-edge because we had to go through two of them. Now, if the multi-edge had actually been inside of the graph and not both of these guys touching the unbounded guy, it could disappear, or if only one of the two sides of the multi-graph had been touching your unbounded face, you wouldn't have gotten the multi-edge there. This one was so tiny, it actually preserved the fact that both the Duel and the original graph were both multi-graphs. But often, one of the two is a multi-graph and one is not, is pretty common too. So hopefully that feels a little bit more comfortable with the Duel. It looked like we answered some of the big questions that you guys had about it. So other questions about the Duel, or feeling more comfortable if you need to draw one on your own? All right, I am not seeing any more questions come in, but if that changes, let me know. One of the things that people use Duel graphs for, and I'll go ahead and throw this in here because we'll look at it actually when we get into Chapter 2 stuff. One of the things that people use Duels for is if you have some original graph, and let me scroll up here to a planar graph that is not a multigraph. Suppose you have something like this guy right here, it's got a bunch of faces, and you want to know something about the faces, whatever it is. The classic example that people give about Duels is if you're dealing with maps, because this was some like actual drawn out maps of like countries and stuff like that. That was something that was done a lot with graph theory stuff, and where some of these properties developed. I want to say it was late 1800s. And cartographers were like, I want to draw a map of countries, and if you've seen old maps, what do? They color code the countries so that countries that are touching each other have a different color so you can see the border line really easily. And they said, hey, I want to be able to color all those different countries something different, at least the ones that have a border in common. That turns out to be difficult to deal with when you're dealing with faces, where the countries would be like a face in that map. So maybe you clean up the edge a little bit and actually just draw straight lines so it's easier, and you're like, oh, it'll be so much easier, and the answer is no, it's not, because you're dealing with a face in the graph that represents your map. Well, if you want to color a face, it turns out to be obnoxiously difficult. However, if you convert into the Duel, notice what happens. Each one of these faces, so each one of the guys that would represent a country, then would represent a vertex, and it turns out there are lots of results of dealing with, if you still wanted to color your countries, color your vertices, where the vertices in the new Duel graph would represent those same countries. Okay? So that's one of the applications of a Duel graph. It's converting the information you actually have into a slightly different format. All the information is still preserved, but with a slightly different format, and then it turns out that sometimes you have more theorems or formulas or properties that are known in this different format. Unfortunately, it does nothing with respect to the edges, but if you're struggling with either your vertices or your faces and you just don't have a property with respect to what you have, convert to the other one, and typically there's a property in one of the two formats, either with respect to your faces or your vertices. But I mentioned that just to give you a heads up that, yes, duels are actually useful. It's not just a thing of like turning your graph inside out. Now, the next thing that we want to cover in this section is the big method that we talked about last time, but we didn't get to, which is dealing with, all right, well, what happens if you have a graph? You'd love to do something like finding its dual, but before you can do that, you have to check to see if your graph is actually a planar graph. Or maybe you want to use one of the properties that only applies to planar graphs. First thing you have to do is establish that you really do have a planar graph. Okay? So this guy here is called the circle-chord method. This is not the only way to determine if graphs are planar. Turns out there's, roughly speaking, 3 ways to determine if graphs are planar. The first one is what we did last time, which is literally move your vertices around until no edges cross. The circle-chord method is something you would do if you can't figure out where to move your vertices to make things work, or in reality, if it's a slightly more complicated graph. Okay? You typically only move the vertices around. It's a relatively simple graph, and you can easily see how to, what I would call, uncross your edges. Please note that's not a technical name. That is just a description. Okay. So if you want to use the circle-chord method, and we'll have several examples to make sure we're comfortable doing this, the first thing you have to have is a graph. Don't overthink that part. Once you have your graph, the very, very first step you have to do is you have to find a circuit that contains all of your vertices. Okay? So please note, this means you need to travel along a path. You start at some vertex. You want to reach all of the vertices in your graph. You can't repeat any edges. You do not want to repeat any vertices either. Okay? So let me make a comment of that. So here, so we want to get to all vertices, and we don't want to repeat, I was trying to be an A, repeat for any vertices. Now, after you found that circuit, what you do is you actually draw this circuit as a really, really large circle. Okay? And what we're going to do is that we're then going to redraw the entire graph. So we're going to transform whatever shape picture the original graph was in, and we're going to redraw it with the vertices in a different orientation. So what people typically do is they'll typically draw a circle first, just a loop for a circle, and then put all of the vertices from your circuit in order around that circle. And you'll see that with the first example. Once you have all of the vertices from your graph on that big circle representing your circuit, then all the edges that weren't a part of the big circuit, you're going to include. Okay? Now, you want to draw them in such a way that they don't cross. So it turns out there's two places that you can draw them in. You can either, and let me make this regular size, you can either draw in the circuit remaining edges inside your circuit, and this is where the circle-chord method gets its name. The circle represents that big circuit, and the inside edges represent what would look in geometry like a chord of a circle. Now, you don't want the edges to cross. So if you start drawing in edges and they're all inside the circle, you may have to draw in an edge or put in an edge, and you realize there's no way to do it except for crossing edges you already have. So this is where you can draw the edge either inside your circle or outside the circle, and draw it in such a way that you don't get any edges crossing. Okay? Now, if you actually can reproduce all of the edges in your graph using this circle-chord method so that none of the edges actually cross, you will get a graph that is planar. And in fact, you would have just created a plane graph representation of your graph, specifically a graph where there's no edges that are crossing. Now, you can also use this method to show that your graph is non-planar, and that'll be a point where you can say, hey, I get this edge, and there's literally no way for me to draw it where it doesn't cross any other edges. That would be where you then write a sentence and say, hey, there's no way I can insert the next edge without getting it to cross. I now have a non-planar graph. The only time this method actually fails is, and let me highlight the part that would fail, the only part where this method fails is if on step 1 you can't actually find a circuit that contains all of your vertices. That's the location or the time when this method actually fails. And if your graph is complicated enough, you can't just rearrange the vertices and get the edges to uncross, and the circle-chord method fails, this is when you would actually go to the third method, which is in a complicated graph a little bit harder to see. But let us look at a couple of examples of dealing with this circle-chord method, and then we'll look to see what that third way of figuring out if a graph is planar or not is. All right, so first graph is this guy right here. So this guy is a bipartite graph. It is written not in the 2 columns that we often have been writing our bipartite graphs in, but it's written in 2 rows, and quite honestly, 2 rows are actually a little bit more common. When you're doing matchings, you normally put your bipartite graphs into 2 columns, but outside of matching, you have it's pretty standard to have your bipartite graphs listed in 2 rows. Don't know why, just that's typically what you see. All right, so if we would like to see if this graph is planar, we're going to apply the circle-chord method and see what we need to do. So I'm going to write the steps over here to the side, mainly because on my screen, I don't want to shrink the writing so tiny for you to see the procedure at the top, but then it's hard to actually see the graph. Okay? So I'll write the steps to the side here, and the first step that you want to do, step 1, don't write in highlighter. It doesn't work well. All right, let's put this in something that will be seen. All right, so the first thing is step 1, so steps. Step 1 is we want to find a circuit And because we have how many vertices? We have 8 vertices. We need a circuit with 8 vertices. So it should be length 8. So let's see if we can't find one. And I'll go ahead and actually highlight the one found. So where would you guys like to start? What vertex would you guys like to start at? You guys have a preference? It doesn't matter. We're going to try to get to all of them. Sure. I like to start at A too. So if we start at A, do you guys have a preference on where we go next? The options are E, F, or H. That's actually the one that I would have picked. So let's go down here to E. And remember, we're trying to get to all of the vertices. So anybody have a guess where they'd like to go next? Hint, you only have 2 options, B or D. Yeah, I would totally pick D too. All right, now once we're at B, we can go to either F or G. Do you guys have a preference? Yeah, I would pick F as well. Just to be strategic here, you know, you're grabbing there the first 4 vertices from the left-hand side, and that sort of strategically tells you, hey, yep, I'm picking up those vertices. Now at F, we only have 2 options. If we go back to A, you close the circuit, and we didn't actually pick up all of the vertices. So at F, we are actually forced that we have to go to C if we want to try to find a circuit that actually picks up all of the vertices in the graph. Now, once you're at vertex C, you have an option. You can either go to G or H. Anybody got a preference? Yep, I would totally have picked G as well. Now, if we're down here at G, we can only go to B or D. If you go back to D, it's not going to be a circuit because you hit B. So let's go ahead here and take us to D. And once you're at D, you're forced to go down to H. Now, this is the big defining feature, the moment of truth. Can we get back to A from H? Is there an edge now that takes us from H to A? And the answer is yes, which means we just found our circuit. So let's go ahead and write this guy down while we're remembering which way we went on that circuit. So we started here at A. We then went to E. We then went to B. We then went to F, then to C, then to G, then to D, then to H, then back to A. I would recommend when you're doing this, at least the first time, go ahead and write down all of those vertices in order. Honestly, I still do it just because it's so easy in step 2 when we start drawing the new picture to accidentally scramble the order of your circuit. Now, you didn't have to pull the same circuit that I did. You could have gone around that circuit in a different order. You could have picked up your vertices in a different order. As long as your circuit actually reaches every single vertex in the graph, you don't repeat any vertices, you don't repeat any edges, you're totally fine to use a different circuit. The only thing that will change is your picture might look a little bit different, but you should still get the same result of whether the graph is planar or not planar. Now, one of the things that I like to do as a second step right here is I like to go ahead and grab the edges that were not included in the circuit. Okay? And when you highlight, like what I did right here, it is really easy to pick out those non-highlighted edges right here. So, for example, we didn't use the edge A to F. Is there another edge that you guys spotted that we didn't use in the circuit? Because we're going to have to actually include it in the redrawn picture of our graph. So these are ones that you want to make sure you grab. I see E to D, yep. BG, yep. Anybody else? Or any other ones that we haven't gotten yet? Because I think there was 4 of them. CH, yep, and CH. Whoops, forgot the comma. All right, so this here is just sort of an aside that reminds us, don't forget these guys. Okay? Yeah, kind of. All right, so next thing that we want to do is we want to go ahead and redraw. So this is where we draw the circle, which is really drawing our circuit. Okay? So here's what people often do. They will often just draw a circle. I'm going to be super lazy so I don't embarrass myself with my circles. And literally draw a circle. And sometimes my circles look a little funky. as if they don't meet, and that's super embarrassing. All right, so when you draw your circle, this is supposed to represent what? It's supposed to represent your circuit. So on the actual circle, we're going to put in our vertices and walk through the circuit in order. You can go clockwise, counterclockwise, it doesn't matter, but you want to put all the vertices around. Now we had 8 vertices, so I'm going to attempt to equally space these guys. Here's the attempt, no guarantees. There's 4, 5, 6, 7. Didn't work, not equally spaced, 8. Okay? But, and here's the key thing, A started here. If I go clockwise around, the next guy would be E. Now, the next vertex here would need to be B. Anybody got a line on what the next vertex would be? What letter should I write next? Yep, F, because that's the next one in the circuit list. Next, we would write C. After C, what should I write? Yep, G. Literally just writing these guys down. So the next one is going to be D. And the last one should be H. Notice if you did it right, this guy coming back to A. Now, each of these little arcs along the circle represents an edge. So at this point in time, we've actually pulled all of the edges from the circuit, all of the highlighted edges from above. So that means the only new edges that you're going to need to add into this picture are the edges that were not a part of the original circuit. So some people will actually do this as a step 2, and these non-circuit edges over here is a step 3. It doesn't matter. You can do these guys in either order you want. Okay? Now, step 4, if you haven't done it yet, we want to add in the non-circuit edges. There's no S in circuit. Okay. And then 5 will be our conclusion. And we'll write that there in just a second. So at this point, we don't even have to look at the original graph anymore. We're only looking up here at our non-circuit edges. So if we look here at AF, well, AF, go ahead and draw that as like a quarter of a circle. Bam, done. So I went ahead and dealt with this one. I'm going to put a check mark by it. We can look at, I don't know, ED. Well, if we look at ED, if we draw it on the inside of the circle, it would cross AF. But could we draw this edge E to D in such a way that it doesn't cross any of the other edges? Yeah, you just draw it on the outside. Don't overthink it. So E to F is just going to be, well, it's a kind of a squiggly line because my hand shook there a little bit. But it's definitely a loop. That's okay as long as it connects endpoints or vertices E to D. That takes care of the second edge. Now, third edge was B to G. If we try to connect B to G inside like a chord, again, it crosses AF, but could we draw B to G in such a way that it doesn't cross any edges? What do you guys think? Can we draw that edge B to G so that there's no crossing, no intersections? Yep, again, you got to go on the outside again. If you wanted to nest it with the other loop, you could. But why bother? Just go around down here. And we actually could have done something as tight to the circle that way on the top as well. Okay? Now, that takes care of the first 3 edges. Last edge we have is C to H. Now, C to H, if we try to draw that one on the outside, notice you would be forced to cross both of the other 2 outside edges. But is there any reason to draw the edge C to H around the outside of the circle? Yeah, there's absolutely no reason. So we'll go ahead and we'll draw this last edge C to H on the inside of the circle. Now, just as a heads up, most people by default try to draw the edges on the inside of the circle, but notice there's no need for each edge. It's its own decision. Should I draw it inside or outside? And it normally doesn't matter. Every so often, if you choose wrongly or poorly, you'll get an edge that crosses that shouldn't have. But in that case, if the first time you get an edge that crosses, go back and double check, see if you could have moved a different edge outside or inside the circle, opposite of what it is, and get no crossing edges. Now, once you've finished putting in all of the non-circuit edges, and you already have all the edges that were part of the circuit, we've redrawn the graph. So this graph has the exact same vertices, the exact same edges that we started with. It's just now in a different orientation on our piece of paper, or formal on our plane. So here's the big question. What do you guys think? Was that original graph, that original bipartite graph, planar or not? What do you guys think? Planar or not planar? So let's call this graph G. So graph G is or is not planar. Ooh, I have got several answers now that I look back up. Yes, this graph is planar, and the reason that it is planar is exactly as one of you guys stated, because none of those edges, once we redrew them, crossed. Notice in the original bipartite, oh good, I did name it G. In the original bipartite graph, what happened in the standard two-row format for a bipartite graph, it looks like almost every edge is crossing somebody. Okay, not every edge. The outer two edges don't cross with anybody else. But most of the edges are actually having some intersection, some crossing with another edge. But we were able to redraw this thing so that there was no edges that crossed. So the original bipartite graph that looks like just a mess of strings is in fact a planar graph. Not going to lie, bipartite graphs are by far the ones that are hardest to visualize for most people of when they're planar or not, just because by default in the standard form for bipartite graphs, you have so many lines that cross. That gets, unless it's a relatively simple bipartite graph, that one can be hard to see just in your head. Although if you can, that's awesome too. All right, so questions make sense? Does this circle chord method kind of feel like something you think you could do? Don't worry, we will have it. We will have more examples. All right, seeing that it doesn't look like anybody's freaking out yet, let us look at another example. So the next example that we have is, well, it doesn't give you a picture of the graph, but it does give you the name of the graph. So this one says, show that the complete bipartite graph on 3 and 3 vertices is non-planar. So this one doesn't ask you to determine whether it is non-planar or not, although you totally could. The question could have been reworded of, is the complete bipartite graph on 3 and 3 vertices non-planar? But it wasn't. I didn't put a question mark at the end. So if you want to determine whether the complete bipartite graph on 3 and 3 edges is non-planar, the first thing you need is the actual picture of the graph. So anybody remember what this guy looks like? Not normally how it's drawn. So bipartite graphs are typically drawn in 2 rows or 2 columns. So I'll draw this one in 2 rows just so it's a little bit smaller up here. So if we did 2 rows, how many vertices should be in each row? So if you were in columns, you'd have 3 vertices on the right and 3 vertices on the left. I'm going to put in rows, so it'll be 3 vertices in the top row and 3 vertices on the bottom row. So let's label these guys. So A, B, C, and then on the bottom, D, E, and F. Now, if you are a complete bipartite graph, what should we do for the edges? In other words, if you were given this question and you put out those 6 vertices so far, regardless of whether you did it in rows like I did or columns like we've done in most of our other examples, what would you do next? How would you know which edges to include here? So there's a bunch of different ways that you can think about it. Key thing is exactly what one of you said. Don't put in any edges in that both start and stop inside the same row. So if you're looking at vertex A has to connect with every vertex in the other row. So 3 here, but no vertices in his same row, or I guess it's an it, so in its same row. Same deal with all of them. So each one of these vertices is supposed to have degree 3. So if we then move on to vertex B is supposed to be adjacent to all three of the vertices in the other piece or the other row, but do not connect vertex B with any of the other two vertices in its same row. And then lastly, we look at vertex C. We go ahead and put in 3 edges that are incident to vertex C, specifically the edges that connect C to all 3 of those vertices in the other row. And notice if you strategically go through each of the vertices on one of the 2 sets of vertices, so in our case, that top row, do we need to include any extra edges? In other words, do we need to walk through the bottom row as well? Or do we have all the edges that we can right now? What do you think? Do we have all the edges that we should have in this graph? Yep. So it turns out with bipartite graphs is because edges have 2 endpoints, and in bipartite graphs, one of those endpoints is supposed to be in one of the sets of vertices and the other in the other set. If you walk down one of the 2 sets of vertices and put in all the correct edges, you don't even have to look at the vertices on the other side, okay? Or in this case, the other row. Now, we want to know if this guy is planar or non-planar. So let us use that same circle-chord method. So I'm going to go ahead and title what we're doing. So use the circle-chord method. So first thing that we need to do when we're using our circle-chord method is we want to try to find a circuit in the original graph that starts and stops at the same vertex, there's one of them, goes through the graph and reaches every other vertex in the graph exactly once. So what vertex do you guys would like to start here? Hint, it doesn't matter, we're going to try to reach all 6. You guys have a preference on which vertex to start with? Sure, I like starting at A too. All right, so if we start at vertex A, where would you guys like to go next? Hint, you've only got 3 choices, D, E, or F. Sure. If we go down here to D, next we can go to E, B, or C. So what would you guys like to go to next? E. I see B coming. Oh, and once we're at B, we can go to next. I see an F, okay, so we could go down here to F. Now, once we're at F, we can either go to A or to C. If you go to A, you'll stop the circuit. So you don't want to go to A because we haven't reached either C or E. So this one, we're forced to go up to C. Now, once you're at C, we're going to be forced again, right? We're going to be forced to go to E because we cannot go back to D. We've already dealt with that vertex. And once we're at E, we've reached every single vertex. So exactly as one of you said, we need to go back to A at this point. Now, let's actually write out the circuit that we grabbed. This is not the only circuit, but this is the one that we grabbed this time. So we started at A, then went to D, we then went to B, then went to F, then went to E, and back to A. Double check, you make sure it's all pretty. This is the nice thing about color coding these guys. When you highlight the edges or indicate in some way that you use those edges, it's really easy to see what edges are not a part of the circuit as well. Now, last time, we also looked at the edges that were not a part of the circuit at step 2. So if we want to do that, we can do that right now. So if we look, so this here is finding the circuit. So the circuit. This one here is the non-circuit edges. If we look at the non-circuit edges, anybody spot an edge that's not inside of our circuit? In other words, the non-color-coded one, and I see there's a couple answers in AF. Yep, AF is an edge. Looks like there's another one. You said BE. Yep, BE is not included in our circuit. And it looks like there's one more. You said CD. Yep, it looks like CD is also one. Double check, are there any other edges that we've missed? Any other edges that are not a part of the circuit that we should grab? I think that actually grabs all of them. All right, so the next thing that we want to do is we want to go ahead and grab our circle. So form, wow, that was trying to be an R. Form the big circle. So this time, when we form the big circle, we actually don't need any information from the original graph anymore. Once we have all the information from this step 1 and step 2, we've got everything we need. So I'm going to go ahead and put the circle over here to the side. We can then, once you have the circle, we put in all the vertices. Here we have 6 vertices, so I'm going to attempt to evenly space these 6 vertices around the circle. They don't have to be even, they just have to be on the circle. That looks roughly even here at the top of my A, and then you can go either clockwise, counterclockwise, it doesn't matter, as long as, notice A is supposed to be adjacent to D. That means on one of these two sides you have to write D. Once you determine which of those vertices is going to be labeled with a D, I went clockwise. That means everybody else is now determined. So after D, D is supposed to be adjacent to B. We follow the curved line to get to B. B is supposed to be adjacent to F. After F, we're supposed to go to C. And after C, we're supposed to go to E. And lastly, we were supposed to, in our circuit, come back to A. That takes care of all of the vertices in the graph. It also takes care of all of the vertices that are what? That are not included in, not vertices, all the edges that are not included in the circuit. Now, we do have 3 edges left. So let's see where we can actually put these guys in. So if we look at AF edge, we could totally put AF, first edge, you can always put AF right here as a chord of the circle. Bam. Now, second edge is B to E. Now, B to E is, here's B, here's E. I can't put the edge B to E on the inside of the circle here or the circuit because it would cross with AF. So where am I forced to put that second edge? Don't overthink it. If it's not inside, we got to put it where? Yeah, we're going to have to put it along the outside. So I'm going to go ahead and put this guy along the outside. That edge is the CD edge. Where should we put the CD edge? Inside or outside? Yeah. Don't overthink it. That was kind of a trick question. So this guy here, and I will go ahead and highlight this in a different color. CD, if you put it on the inside, would totally get a crossing. So that means you can't put the CD edge on the inside of the circle. But if you put the CD on the outside, that's going to go around the top E right there. So that's also problematic. You have both of those two locations, either inside or outside the circle, not working out. In other words, you're forced to have an edge that crosses. This right here tells you that what conclusion do we get? What do you guys think? Yeah. So this one here, the conclusion is that this graph, this complete bipartite graph on 3 and 3 vertices, is not planar. This is actually one of the smallest non-planar graphs that we have. It depends how you count smallness, whether you're looking at number of vertices or number of edges. There is a graph that's smaller or has fewer vertices. I'm trying to think how many, but that graph has one more edge than this graph has. So they're roughly they're the 2 smallest graphs that are non-planar. It turns out if you have a graph that is a copy or a subgraph of K33, right here, a smaller non-planar graph, is itself also going to be non-planar. It's one of the reasons we look at these smallest non-planar graphs, because if we can find a copy of K33 in a larger graph, what that tells you is you're always going to get one of these situations where the edges start crossing. But this guy here, K33, the complete bipartite graph on 3 and 3 vertices, is one of the smallest graphs that's non-planar, which means if you have only, say, 3 vertices, this guy's going to be planar. You just have to figure out how to redraw the edges. Turns out, same deal, if you have 4 vertices, all graphs on 4 vertices are planar. You just have to figure out how to redraw your edges. So let me go ahead and give you that extra thing. So note K33, and I'll give you the other graph too. K5 are the smallest non-planar graphs. And that actually is the lead in to the third way of determining whether graphs are non-planar or not. And that way, and we'll write it down in just a second, but that way is if you have a subgraph in your larger graph, it's either K33 or K5, you actually are non-planar because these two guys themselves, your subgraph or a part of your graph, is also already non-planar. But notice K5 is what? It's the complete graph on 5 vertices. So if you have 4 vertices or less, or if you have 5 vertices or not a complete graph, you are looking at graphs that must be planar just because they don't have enough vertices or edges to not be planar. That's a fun little fact. Now, in order to get up to actual condition of when we're going to use K5 and K33 as a way to determine whether your larger graph is planar or not, we actually need a definition first. And this definition is something called subdivided. Instead of being super proper, I'm going to show you a picture and just give you a quick word definition. So this here is simply a graph. So you start with a graph, and you've added in strategically extra vertices. So with extra vertices, write down how those vertices were strategically extra. So let me get you an actual example first. So let's actually tag this in red so it's easy to tell that it's an example. And then we'll see if you guys have a guess on how we need to add in the vertices and what the special way is to add in the vertices. So suppose you have the original graph is actually label it G. And I'm going to put it on 4 vertices. And I'm just going to draw a little planar graph. We're only looking at the buzzword of subdivided, nothing about planar or non-planar at this point in time. Now, I'm going to claim that the second graph is the original graph G but subdivided. See if you can spot the difference between these two graphs. So the first one looks like a box with one line through the middle. Second graph looks the exact same way. So anybody have a guess on the strategic location or what the key difference is between the original graph and its subdivided version? Yep, the first thing is just definitely more vertices, but it's not any old more vertices. Those extra vertices have to be somewhere. Yes, so the key thing of where those extra vertices are is you've taken existing edges and you've literally subdivided, this is where the buzzword comes from, you've subdivided those edges or split those edges by inserting extra vertices. Now, we subdivided 3 of the edges of this original graph. The top one, we just inserted 1 extra vertex, and that's totally fine. The one here that's vertical on the right-hand side, we've subdivided the 1 edge into 2 edges. And this guy that looks diagonal, we've actually subdivided it by inserting 2 extra vertices. So here's the key thing with your vertices. They have to go, the extra vertices, on existing edges. That is the key thing. Now, technically speaking, in the subdivided graph, you are getting more edges because you've broken like a long edge into smaller pieces. But from the picture standpoint, it looks like you've just drawn those vertices on top of edges that already exist. Okay. Now, we actually care about that buzzword subdivided not by itself because it's used in the definition of something. And that something is something called a configuration. So a G configuration, G is actually the name of the graph that you started with. Okay? So a G configuration is a graph, or if you prefer a subgraph, which can be obtained from the original graph G by subdividing its edges. So notice this first graph we called G. Over here after the arrow, that other picture with the 3 extra edges, this would be a G configuration. So that's the tie-in between the two. The configuration says overarchingly, it looks like the same structure. So yes, I know there's extra edges and extra vertices. If you sort of close your eyes and squint and ignore these edges, these vertices that look like we really didn't need them, you get back to the same picture. And that's totally layman's terms. Those are not technical details out of class description. Now, we care about 2 special types of configurations. We care about a K5 for a complete graph on 5 vertices configuration and a K33 configuration. So if we look at these 2 guys, let us look at examples of these 2 guys. So if you look at a K5 configuration, first I'm just going to draw K5. The K5 is typically drawn, roughly speaking, in a circular orientation. So around the outside, it sort of looks like a pentagon. The inside, it looks like a star. I missed the vertex. We'll make it bigger and pretend we actually got it. All right, so there's K5 originally. Now, to get a K5 configuration, it's totally fine if it's actually just K5, but the configuration part allows you to take any edge you want and actually split it up by inserting an extra vertex on that edge. So in other words, maybe you take this edge on the left and you split it into 2 edges by adding 1 extra vertex. Maybe into now 4 teeny tiny edges. Okay? So this would be now a K5 configuration. It doesn't matter how many vertices are along what would be a normal edge in the K5 graph. In the configuration, you can have just the 1 edge, like up here. You can have really 2 edges stacked together, 3 edges, 4 edges, etc. Now for K33 configuration, you can do a similar thing. Okay, just a second. Can you guys hear me now? Okay. So it may be that my cable is not connecting correctly. So let's try to fix that. Got something on it so it won't move now. All right, so what was the last thing that you guys heard? Okay. So here, the only thing, where is it? The only thing that I was doing here is put the original K5 graph and just added in the extra vertices. And the only thing that I mentioned there was it didn't matter if you had no extra vertices, if you had 1 extra vertex, 2 extra vertices, 3 extra vertices. It didn't matter if you had extra vertices or not. Okay? So the only thing we were doing here was just creating a K5 configuration where you have the original K5 graph, and then maybe some of the edges look like they have extra vertices. And that's the only thing that we've done while we've been on this particular picture. So hopefully that gets all of you caught up to speed. If you have questions, throw them out, especially if the sound was frozen on you. Okay. Now, if we do the same exact thing with the complete graph on 3 and 3 vertices, first thing I'll do is go ahead and draw in K33. So this is that same graph we just had where each vertex has degree 3. Each vertex on one side is connected to all the vertices on the other side. And if I could draw awesomely, you would have no squiggly lines there. It didn't happen. Now, this guy here is actually the graph K33. So totally fine if that's the guy you want to call a configuration. But typically you don't bring in this buzzword of a configuration until you have at least one of the edges that has been subdivided by an extra vertex. Okay? So this here would be the simplest version of the configuration, which is two edges by exactly what can be that simple all the way up to having edges by the first. That leads into that. All right. Okay, can you hear me now? Okay, so it sounds like some of you are having sound issues and some of you are not. So that may or may not be on my end. So if your sound goes out, let me know and I'll try to restart it on this end because that does seem to help some of you guys. So let's cross our fingers and hopefully it doesn't happen too much in the future. Where were we? Right, configurations. Let's actually get to the thing that we cared about, which is Theorem One. Yes, it is another Theorem One. Yes, your book keeps renumbering theorems using the same number. Now this one here is also was contributed to Kuratowski. So sometimes people just call this Kuratowski's theorem, as I completely just fell down on saying the syllables. But anyway, what it says is this is a way to determine whether graphs are planar or not, and this is the official way of determining planar graphs or not. The other two ways that we've done both today and yesterday are nice methods. They're nice algorithms of finding out whether graphs are planar or not, and I'm not going to lie, they're easier than this official method in Theorem One. Okay, so either that circle-chord method or last time when we just rearranged the vertices. So this one says a graph is considered planar if and only if, so this is the criteria, it doesn't contain a subgraph that is either a K5 or K33 themselves, or a K5 or K33 configuration. And he just said configuration for all of it. The question is a configuration of some graph to graph that can be, I like your quotes, smoothed into a graph G. Roughly speaking, yes, if you mean smooth, means you sort of erase those vertices that look like they're in the middle of an edge. Yeah, that's a good way to think about it. Okay. So let us look to see how this is all put together. And, oh, a comment. So one of the comments is even though K5 and K33 do have a tendency to, roughly speaking, be the same size, they're one different in number of vertices, one different in number of edges. K33, 6 vertices, 9 edges. K5 is 5 vertices and 10 edges. It turns out with the complexity of how their edge structure to vertex structure is, you typically get a copy of K33 occurring more frequently in your, for lack of a better word, smaller graphs or less complicated graphs. So in a lot of the graphs that you guys will see, you'll actually see K33, I can't speak, K33 popping up probably a little bit more frequently. But K5 configurations totally come up too. All right, so suppose you have the following example. So this guy looks really similar to graphs we've seen in the past. It looks like two squares, one inside the other, and then some lines between the two squares. Now, notice here, we've got a grand total of, what is that, 12 edges. We've got 8 vertices, and we've got only one edge right here that is crossing one other edge. So the question, of course, is there some way that we could redraw these vertices so that this edge that's currently crossing edge DE doesn't? Can we maybe twist this inside bit around? Maybe flip it a little bit? If we flipped H and F, would that help? Well, it definitely would help this one, but then we get another crossing down here. So maybe you play around with it for a little bit and you try to redraw the actual vertices. Okay? In this particular case, I'm going to go ahead and actually use the circle-chord method, and then if we get a planar graph, awesome. If we don't get a planar graph, let's see if we can't figure out what configuration we have. Specifically, it would have to be a K5 or a K33 configuration. And when I do this, let me go ahead and show you one of the other ways that people draw the circles in the circle-chord graph. So first thing that you'd want to do in your circle-chord method is you want to go ahead and find some circuit that actually goes through all of your vertices. What do you guys think? Is there a circuit that goes through all the vertices? Don't overthink this one. Yeah. So if you start at A like we have in the past, maybe you go around the outside. I would do that because I'm totally lazy. Once you get at D, don't go back to A. You'll stop the circuit too soon, so you have to then, you're forced to go into E. Now, once you're at E, where do you guys want to go? F or G? Don't lie. Don't go to F. F, or H was what I meant to say. So if you go to F, next you're forced to G, you're forced to H, and once you're at H, we visited all the vertices, so back we go to A. This one alphabetically worked. And part of that is how I have a tendency to label the vertices just going around in a circle. So this one, our circuit, our big circuit is A to B to C to D to E to F to G to H. Please note that that being alphabetical is 100% coincidental based on how I label the vertices. Typically, it's not alphabetical whatsoever. Now, the second thing that we want to worry about is our edges that are not in the circuit. So anybody spot some edges that are not incorporated into this one large circuit? It looks like there's A, D, so I'll do the easy one. Anybody spot another one? See, F. Nope, not an F, G, but there's F to who? F to B, yep. Oh, I see a couple more coming in. G to C, yep. And E to H. It looks like there's only 4 of them. You guys spot any more than those 4? Yeah, I'm not spotting any more either. I think we got them all. All right, so once we have that, we're good to go in terms of drawing. So now we're ready to put this guy into circle format. Now, one of the things that people like to do to really highlight that these are edges for your circuit is sometimes instead of drawing the big circle first, they'll do something like this. In our circuit, we have this first edge, A to B. Then we have A to C. Then we had C to D. Then we had D to E. Then we had E to F. Then we had F to G. Then we had G to H. And then H went back to A. And notice in this case, I went ahead and drew in straight lines, those straight lines representing edges. Now, putting this all together, we still need to deal with these 4 edges. So A to D, we could totally put in A to D. I'll go ahead and put it on the inside of the circle because it's the first edge we dealt with. F to B. Well, F to B would cross if it's on the inside. So that one I actually do need to curve because outside edges you pretty much have to curve. Third guy is G to C. Now, G to C right here actually, where is G to C? G to C, if we try to do it on the inside, would in fact cross AD edge. But if we did it on the outside, it would also have to come and cross this BF edge. So this one right here has a dotted line. And then this intersection right here. Now, what does that tell you? That tells you in terms of our conclusion, that we should get that this graph is non-planar. Now, notice here, we didn't put in that last edge. So we're going to do that here in just a second. When you get the crossing like this, notice this crossing actually looks really, really similar to who? It looks really, really similar to the same sort of circle, 2 edges crossed on the inside, 1 edge on the outside that we got when we got a K33 configuration. This, or when we did this same circle chord method for K33. That means this guy is going to actually have a K33 configuration. Now, K33 only has 6 vertices. So I'm going to highlight the 6 vertices that are in play right here. A and D has the inside edge. B and F has the outside edge. And C and G also has an inside edge right here. And notice we have then 2 vertices that were not highlighted. So I'm going to take those 6 vertices and try to draw a K33 configuration. Okay? So A. So A up here is in terms of these 6 vertices adjacent to B and D, so B and D have to be on the other side. There's B, there's D. Now, if we look at B, B is adjacent to both A and C and F, so C needs to be on the other side, and F is theoretically on the other side as well. So B was connected to A, C, and D. C and F. And then we say, oh dear, because why? Because A here, if we actually had a true configuration, we would need A to be what? It'd need to be degree 3. Well, it turns out A here, if we need to include it in the configuration, has to be connected here to H. So that means the 6 vertices that we picked here, well, they're not the right 6 vertices. So if we have to then go back and include H, let's get rid of 2 of the vertices, and I'll actually just show you which the right 2 ones worked. We needed H, C, and I'll go back and just highlight the right ones. That didn't work because I need to unhighlight some things. And yes, this would work with any circuit you grabbed. The ones that we want, F and G, are the ones that actually are going to, are going to be the ones that are making the configuration. All right. So we'll go back and erase these guys as well. F was the only one that should be erased. Now, how would you know to actually do that if you were doing this on your own? The same reason that I saw, hey, I had to have A have degree 3, that would be a clue to redraw these guys. It turns out this guy would need to be E on the top, and on the bottom here would need to be H. If you go in and start connecting them, notice what will happen. A is adjacent to B, A to D, and to H, so no extra vertices on any of the lines incident to A. C, however, C is directly connected to B. C is supposed to be directly connected to G. G's not over here. Where's D? C is directly connected to D. C is not connected to H, but notice G is connected to H. So this tells us right here, we actually put G from C to H. Now, last one is E. E is directly connected to D. E is only degree 2, so you got to watch out for that one. So E, oh, that's because I don't have the last one. Whoops. So E is directly connected to H. Don't forget about the one you didn't put in the picture. That's always bad. Okay? And so E here is what? Not directly connected to B, but E is connected to F. That isn't listed in the graph. So E to F to B, and that would be your configuration. In this particular case right here, it turned out the entire graph was a K3 configuration, and that's the easiest case possible. So the question is, why couldn't you have added H between A and G? You could have. So this is not the only configuration that could have come. Because we were so tight on time, I went ahead and grabbed one that I'd found before class as opposed to one that we totally worked out together over here, just so that I could draw it quicker for you guys. But yeah, there's more than one way to do it. The only thing that you have to worry about is you make sure that the 2 edges that you actually have stacked together here have to actually match with the edges in the graph itself. So hopefully that makes sense. Notice it's the end of section 1.4. So the only thing left in section 1.4 is dealing with Euler's formula. So we'll do that at the beginning of next time. Okay. So I'll hang out for a little bit if you guys have questions, but otherwise that is it for today.